I want to kind of like just follow through on my last promises to y'all a few minutes ago and show you more details about that if it helps to clarify a little bit. So we talked about this idea of signal detection theory, just kind of what we're looking at here on the screen, okay? And we talked about how some of the early genesis and etiology, or basically beginning of this field of investigation and that brought us signal detection theory came from the attacks on Pearl Harbor. We had the radio receivers that were missing the incoming bombers, and we wanted to understand why that might be happening. All right. So we came up with this idea of signal to noise ratio. Right. Signal in this case, or hits for the signal, would be planes, and noise would be birds. We talked about that in the context of cancer detection, of memory experiments. Okay, and this idea that you can have a liberal to conservative criterion, and that it can shift. You can change how you place that criterion of what you decide to call a hit or of correct rejection or whatnot as you do the task. Okay, and we talked about how that same principle is evident in CT, MRI neuroimaging, and other things like that. So we looked at this basic framework here where we had our distribution of responses. So in this case, when a tumor is present, that would be a hit. In this case, it would be when the tumor is not present. And again, we can frame our internal responses in that regard. Now, we talked about creating this little chart of hits, false alarms, missed correct rejections. That's all the good stuff that we had on the screen. So we already looked at that a little bit. And this is one way to characterize the respective areas that are going to be hits, misses, correct rejections, and false alarms. Okay, so it's just the same information that we've drawn on the board, just a little bit cleaner. And so we talked about how you can begin to quantify the ability for our receivers, or in this case your research participants, to detect signals, or in this case old information, from false alarms, or that which they were operating. Okay, so we can take a little bit closer look at how this works in memory, okay? Because remember, we've talked about this idea that you either have one process in memory, okay, whereby you have the ability to discriminate or deprime, okay, based on old and new distribution of information, okay, but it's ultimately one memory process. But then that dual process view is characterized here, up on top, where you have old and new discrimination here for familiarity along our confidence scale, but only on the edge here does recollection happen, and it's sort of a threshold idea. That is, it doesn't bleed over into the other confidence levels the way that your familiarity confidence levels will. Okay, so that's the basic contrast between those theoretical models of how cognitive psychologists understand human memory. Okay, now here's kind of what we talked about. Now, if you'll indulge me in the back and shut off some of those lights, I could probably give you guys a better view of this slide, if you don't mind. Does that help? Better? Okay. So the question was, how do you make that ROC curve? What is it really reflecting? So when you have a confidence memory scale and an old new recognition task, okay, where they say they're sure they're old or they're sure that it's new, you add up all the times that they say each of those responses in our confidence bins. So in this case, you have your confidence bins, 6, 5, 4, 3, 2, 1, okay? Now this is in green on the bottom, so that means it's new items. And the blue are the old items that were studied. So this is how many times they said, I definitely think it's old for an old item. So these are our hits, right? Same thing we've kind of looked at before. These are going to be our false alarms. Here's going to be our correct rejection, so a lot of those. And here's going to be our misses. Now, this is a normal, healthy subject who doesn't have amnesia or type of memory problems. And we know that because they mostly get everything right here, and they very rarely make these mistakes. Right? Okay, so what we can do, right, is plot our probabilities of a hit, P hit, versus the probabilities of a false alarm, along each of these competence scales. Okay? So here's what we're looking at. See how this just turned yellow? It's corresponding to this y-axis. Okay, now look at this. Okay, now this is yellow down here. False alarm is corresponding to these. These are false alarms. So just kind of orienting again to the scales. Is this a little helpful? Okay. So we set our criterion very strictly. We're only going to talk about the really things that they're absolutely sure of. Okay? Now in this case it's a ratio, right? Well, in all the cases it's a ratio, but in this case that ratio is this big huge blue bar to this tiny little baby green bar. All the way on the right hand side. Okay? Now when you do that, you get that mark, just like I drew on the board. Okay? That's the ratio there between this and that. And as we move this way, these dots start to move this way. All right, do it again. One, 2, 3, 4, 5. Draw a line. 1, 2, 3. Is that helpful? Kind of bring it together a little bit. So it just, that's how this line moves over, based on including more and more criteria. Connect those lines and you have your receiver operating characteristic curve. Now we talked about this being that line of chance performance. Now in this case it's a very good performance here because they have that bow line away from chance. Okay? You have that y-intercept there, according to Recollection. Okay? And that's kind of your representation. Now remember we talked about how do you get a rodent to tell you its confidence? Okay, this is the study I was talking about. Okay, where you get them to be trained so that if there's a new scent during the memory test, like that new item and this new smell, they know that they should dig for a reward in that cup. But they also get trained so that if it's an old scent, they can go get a reward of a Fruit Loop in the back of the cage. Okay, and based on that, we can do this manipulation that we talked about of changing how deep they have to dig down to get a Fruit Loop, and also changing the reward of how many Fruit Loops they get. 3 whole Fruit Loops or just a little tiny fraction of one. And so as all of you imagine, right, you're not going to do a ton of work for a tiny little baby reward unless you're really, really sure you're going to get that reward. Right? That's how you can tell how confident the rat is. You look at its behavior, at how it explores its environment. Does that help to kind of pull some lines together? Okay. I thought it was really cool. It's a really nifty thing. And remember, we looked at these ROC curves now, and this is for the rodent. And just like I mentioned earlier, when they're control condition, before they get surgery, they get a nice recollection intercept of the y-axis, and this bow shape away from chance. And at the same time, after you get the hippocampal lesion in red, they still keep familiarity because you have this big D prime away from chance performance. But look at the recollection estimate. It comes all the way down to basically 0. Now this is in rodents, and it corresponded really nicely to the work that Andy Onelinas did in 2002 with humans who had hippocampal damage. And that's what we're looking at down here in this bottom graph. Same thing, normal healthy humans like most of you guys, they're going to be this blue line. Again, we get this nice healthy shape of the bow away from chance as well as this y-intercept. But when humans had hippocampal damage, their recollection estimate went down to nothing. Meanwhile, they kept the ability to do familiarity-based recognition. Yes, Brittany?
Is the bow, like the peak of the bow the most familiar, or is it the fact that when you get farther away from recollection that it's more distinct on the
It's more familiar, because if you look back here, if we scroll back to our initial thing, look at what happens. When the bow doesn't really, this bow up here, this doesn't really start happening until we start including these middle trials. See? So that's what it's reflecting, those other levels of familiarity. Okay, so, and that's just comparing the rodents to the humans, and that's pretty cool. And this is just some of the hippocampal damage that the humans had And we'll be able to work with some of that data as well. And anyway, so that's kind of what they did, and we'll work with some EEG as we get more in depth to things. Okay, and of course those are our signals that we talked about: the midfrontal effect, the late parietal effect. It's early in time for the FN400, about 300 to 500. A little bit later in time, from about 6 to 8, 6 to 9, and it's going to be left parietal distribution. And so we've talked about that before and how that made those predictions. So anyways, let me escape out of here. And are there questions on that? That kind of helped to tie together.